So we have the pleasure to have Andrea Nahmod. Andrea is professor of mathematics at the University of Massachusetts and Amherst. Her research lies at the interface of nonlinear Fourier and harmonic analysis and the theory of partial differential equations. Some of her recent work aims at gaining a quantitative understanding of the propagation of randomness under the nonlinear evolution of dispersive PDE. Andrea is a fellow of the American Mathematical Society, a recipient of the Sargent Fall Fellowship at Harvard Radcliffe Institute for Advanced Study, and of a SIMA Foundation Fellowship, among several other things. So today, Andrea is going to talk about Gibbs measures and propagation of randomness under the flow of nonlinear dispersive PDE. Please, Andrea.
Thank you very much, Felipe, and thank you very much, Elena, and all the organizers for the very kind invitation. It's a pleasure to speak in this seminar, and I mean, I'll try to do my best to sort of like be a little bit broad. Some parts are technical. So let me start by minimizing this window so I can see my own screen. Okay, here. So let me start by sort of like saying like where this talk is. So this talk falls under the general umbrella of trying to understand and describe how randomness affects the behavior of the solutions to evolutionary PDE. So you know, that depend on time. So the randomness sort of in the problem may come in many ways. I mean, and this is an old subject, but two ways that are common and are like, you know, when the randomness comes from the equation, such as when you have a sort of an additive noise or multiplicative noise or some other type of noise, or when your data is random. And so random data which obeys some canonical law of distribution, then that's another way of injecting randomness into a problem. And this sort of naturally arises when you study wave phenomena in a variety of subjects, such as when you study Gibbs measures. This is related to sort of the constructed quantum field theory or also statistical mechanics, or for example, in the theory of wave turbulence, or sort of when you simply study the Cauchy theory in certain regimes, as we will see. And so the questions are natural, and what is beautiful about it is that somehow the mathematics that you need to study these problems come from a lot of different areas, not just PDE and sort of Fourier and harmonic analysis, but of course probability, so some analytic number theory, combinatorics, stochastic PDE, geometry, and so on and so forth. So the goals for the talk, the main goal is to discuss actually the second one that I put here, which is I went the wrong way, which is the random initial data problem for dispersive PDE. And the main goal is that I want to tell you a little bit about the background, but try to go through two new things that we have developed with Yu Deng and Hei Yue, my collaborators. One is to describe what we call the theory of random tensors, which is in some sense, as I will repeat later, is kind of the dispersive counterpart to the theory of regularity structures of Martin Herr, that was developed in the context of parabolic stochastic PDE. And so I want to tell you a little bit about the theory of random tensors and also the method of random averaging operators. And then at the very end, depending how much time I have, I will discuss some open questions, but I also want to maybe tell you at least the statement of a new result that should be posted early next week on the archives, in which now, not just with Yu Deng and Hei Yue, but also joined by Bjorn Brinkman, we were able to prove the invariance of the three-dimensional Gibbs measure, but under the flow of a nonlinear wave, the cubic nonlinear wave equation. So this is what is called, sort of also referred as the hyperbolic phi-4-3 model. And so this is I'll say very little about this at the very end. So let me start by saying that sort of the random data problem can be viewed as the study of propagation of randomness. So because you start with some random initial data, which is distributed according to some canonical law, like a Gaussian law, in which so that data has independent Fourier coefficients. And what you would like to know is how does this random structure gets transported as under the nonlinear dispersive flow, okay? And so some fundamental questions that you can ask is, okay, what is the optimal regime? I mean, for what type of regularity of these random data can you show that you have existence and uniqueness of solutions, at least local in time, what is the optimal range for which you can do this, and why? Okay, not just doing it for doing it, but you want to understand why is that so? And then you want to also understand, actually, if you can have a much finer description of the solution in terms of the random structure of the initial data. So you know, if I give you random data, then the linear evolution of that random data, you know exactly how it looks like. But then you want to know into high orders, is like how does this initial Gaussianity has propagated, okay? So what happens at higher orders? And what is exactly the description of the solution, if you can give a description of the solution beyond the linear evolution, okay? And so these are very important questions. And also what you would like to know is if for the PDE that you're studying and at the level, in the right dimension and correct regime, if there is formally an invariant measure, then you want to know whether you can justify the invariance of this measure, okay? And so together with you, Deng and Haitian, we actually provided answers to these, all these questions. And from now on, I'm going to focus on the sort of like the showcase all of this in the most perhaps central PDE, or most sort of that appears most of the time, which is the nonlinear Schrodinger equation. So let me tell you a little bit about the deterministic, very little about the deterministic context. I am always going to be in the periodic case, so on the square torus, and so this is the sort of the linear Schrodinger equations with powers p. I'm going to call it p and ls. So p is always going to be odd, and here you can have a plus and minus, but for the local theory, it doesn't matter. For the Gibbs measure problem or global, does. So I'm always going to choose the plus, which means that the equation is defocusing. And so for this equation, we have a conservation of Hamiltonian and a conservation of mass. And I want P odd because I want the Hamiltonian always to be coercive or positive definite. And so it's very well known that there is a deterministic scaling associated to this equation, which is the Sobolev space HSCR, which I call here SCR for critical, which is the dimension over 2 minus 2 where p minus 1. And so a basic theorem, which follows essentially from what is known as the dispersive, as the Stricher's estimates, which are the dispersive estimates in this context for in the periodic case, is that if this number is bigger or equal than 0, then for any regularity that you take the data, for any U0 in HS with S strictly bigger than this number, then you have the existence and uniqueness of solutions locally in time. And this essentially follows from this Stricher's estimates as was done by Bourgain in '93 and Bourgain and Demeter in 2015. And there is also examples that tell you that if you are below this critical regularity, then there is some form of imposedness that occur. And there is a paper of Chris Poliander and Tao, and also maybe not exactly in this context, but there is also important results of Biaggioni and Linares, and Felipe has also worked on imposedness and some other people. So the point is that, okay, you have this issue with the imposedness, but what happens is that if you switch your point of view, and instead of taking every possible data in HS, you actually try to think of this problem from the almost sure, in the probabilistic sense point of view, then you can actually cross this scaling barrier. And this was sort of like done first by Bourgain in '96, who showed that if you consider random data in some deterministically supercritical space, right? So if you are really below this, but your data is random, then you actually can prove that almost surely you have strong solutions. So before this work, people knew that you had weak solutions, but nobody knew anything about uniqueness. And he actually proves that almost surely you can have existence of a strong solutions. In this paper, not just local, but in this paper, he also did globally. Okay, I'll mention later. So this approach of actually considering random data is meaningful because it's kind of like a link to statistical mechanics, or in which you actually want to view the problem. The point of view is that instead of considering an individual solution, you're interested in a family of solutions that are distributed according to some, say, Gaussian law or some canonical law. So this is actually very natural. So let's talk about what is your random data. So your random data, the typical element that I'm going to consider is going to be given by this random Fourier series, where these GKs are complex Gaussians, which are normalized and sort of have mean zero. They're like and you can take a Gaussian, so you can take sort of like something that is uniformly distributed on the unit circle. It doesn't matter. Okay, you can take whatever you want here. And so let me pay attention here to the relationship. So here you have a power alpha, and then this alpha is going to be some s plus the dimension over 2. And this s means that if you take this expression, then this function f is going to belong to h, almost surely it's going to belong to hs minus epsilon for any epsilon, okay, for where the s and the alpha are related in this fashion, okay. So the law of distribution for this f function f is formally given by a Gaussian measure, which is the exponential of minus the h alpha norm square times the Lebesgue measure. And of course, this as written makes no sense. This should be understood as the weak limit of finite dimensional approximations, right? I mean, you cannot define the Lebesgue measure in infinite volume. But suitably understood, this is somehow this data is exactly sort of given by this Gaussian measure. And so I want you to remember this, that alpha is s plus d over 2, that alpha is the power that you put here, and s is where this function is in hs minus. So it's just below hs. Okay. So I want to try to understand, or we want to try to understand in the probabilistic setting, okay, what is the right threshold that one should expect that you have local well-posedness. So in the deterministic sense, people know this, and this comes from this scaling, this deterministic scaling, which is d over 2 minus 2 over p minus 1. But when you take random data, this is not the right scaling, or these are not the right lens through which you want to measure what is the optimal range for which you can get local well-posedness. So to answer that question, what we proposed was this notion of probabilistic scaling, which has the following heuristics. Okay, so it comes from the following heuristics. Suppose that you take random data, but your random data, you take it very easy. Take something which is sort of like all the frequencies are sort of you fix a frequency scale n, and all your frequencies are of size sort of order n. And then I put the denominator here outside, n to the minus alpha becomes here outside because k is like n. Alpha is still s plus d over 2. And as I said before, and now this is a single scale, so f has unit size, this given like this, has unit size in hs. So you ask the question, right? If I want the NLS to be locally well-posed, then what should happen is, okay, you have the linear evolution of this function, but then what should happen is that when you take the second iteration, so when you take the Duhamel, this I is the Duhamel, so you take the Duhamel of, say, the p power, when you plug in here the linear evolution of your data, then you would like the second iteration to stay in HS. You start in HS, the linear evolution is in HS, and then you want the second iterate to be in HS, right? Sort of when you start doing your Picard scheme. So then you say, well, when does that happen? Okay, for what S can I guarantee that this stays in my space HS, okay, for a fixed time? So you fix T, and you calculate the Fourier coefficient of this, and that's essentially in fixed time, so the Fourier coefficient in space, that's essentially n to the minus p alpha times the sum, okay, of k1 minus k2. So the plus minus come from, these are complex values, so that you might have a bar or no bar. So it's u bar, u bar, and so on. And then you have your random variables, which also have, right, u bar, up to the power p. And so here 1 over omega, this is Japanese bracket. So 1 over omega is what we call the resonant factor. And it's actually given by when you take the Fourier size of the Fourier coefficients of the linear evolution, okay? And the plus minus correspond exactly to the bar or no bar. So minus when you have a bar, okay, whatever. So this is k squared minus k1 squared and so on. So now, just for simplicity, I'm going to think that this omega is any constant. It's a constant. It's a number fixed, and I can fix any number you want. 10,000, 1,000. I'm going to fix. I put Japanese brackets, so I'm going to fix 0, just for simplicity. But you can fix any number you want. So in some sense, I'm sort of like trying to understand, sort of like high into high interactions. So if you plug in this number 0, then your expression in Fourier transform looks exactly like this. Okay. So now I'm going to assume that this is stay independent. So that means that k1 is never k2 and so on. So that I always have independence of these random variables. And so what I know by the central limit theorem, or sort of using sort of large deviation, is that if I want to know what the size of this is, the size of this object is essentially n to the minus p alpha times the square root of the cardinality of this set. That's exactly what that's exactly what you get when you do your large deviation. And the square with this is exactly because you have here randomness, that you have what I call a square root gain. So in other words, instead of having that the size of this is n to the minus p alpha times the cardinality of this set to the power 1, which is what you have in the deterministic case, here you have you have a square root. Okay. And so what that says is that then n to the minus p alpha, you get, if you by dimension counting, you count the cardinality of this set, you get that this is n to the minus p alpha times n to the pd minus d minus 2 over 2 divided by 2. If you were in the deterministic case, you wouldn't have these two. And then you ask the question, what do I need on S so that this is still bounded in HS? And you do your calculation that then what you need is that then this number plus alpha, which is plus S plus D over 2, should be negative. And that happens if and only if S is bigger or equal than minus 1 over P minus 1. And this is what we call the probabilistic critical scaling index. So the probabilistic, in the probabilistic scaling, this is what is going to be the critical index. So what we sort of conjecture is that if S is strictly bigger than this, that's what we should correspond in the probabilistic setting to being subcritical. So it should be that if S is bigger than this number, then in the probabilistic sense, you always have local Wolf-Hausness, okay? And this is a number that is always lower than the deterministic one, right? So actually, if you repeat this calculation and you have all ones here, so you don't have random variables, that's the calculation that you would do in the deterministic setting. And then the number that you will obtain here, if you remove these two, will be exactly the green number, the d over 2 minus 2 over p minus 1 that I told you before, okay? It gives exactly the same. Okay, so we define this as being our probabilistic scaling, and then our first theorem is exactly that we prove what we conjecture. So this is the theorem that we prove that answers in some sense the first two questions that I asked before. What is the optimal range? And actually it answers more. It gives us a precise description of how the solution looks like. Okay, so the theorem says that for any S strictly bigger than this SPR, so in the full subcritical regime, then the PNLS on the d-dimensional torus with random data, as I showed you before, has a local in time unique strong solutions. And moreover, we have a precise description of how the randomness propagate, at least for short times. Okay, so roughly speaking, okay, what we have is that if we were to expand this solution to NLS in Fourier space, then our Fourier coefficients will have exactly this form, where this is somehow an expansion of some coefficients. You think of T as a parameter, so you have some coefficients here, which is what we call the random tensors, times sort of multilinear Gaussians. And the property that you have here is that these random tensors remain independent from these Gaussians, okay? And then you have a remainder, which according to how long you want to do your expansion, this can be as smooth as you want, and is small in L2. So the length of the expansion that you do is related to how close you are to your probabilistic scaling. How close you are, then the closer you are, the longer the expansion, but also how smooth you want your remainder to be. Okay, so in some sense, the D is linked to how close this S is to this, but also how much regularity you want in the remainder. And so these quantities, as I said, these are what we call the random tensors, and these are highly nonlinear objects that actually carry all the information about the low frequency components of your solution. So here you have somehow the high frequency components, and here these carry with you the information about the low frequency components of the solutions. And as I said, this is independent of this. Okay, these are going to be in some sense Borel functions of the Gaussians with a K sub L, which are like much smaller than the maximum of the size of all these frequencies to some small power. Okay, so they are going to remain dependent. So this is essentially the answer we make, but this is actually what we end up proving. Okay, so we make this answer, and this is what we prove. And so the convergence of this, okay, the convergence of this Fourier series is totally determined by the properties of this. I don't know how to get rid of this. Sorry, I have something covering my slides. I don't know if you see it or you don't see it. I don't know. You see this black thing that I'm moving? No, it's only me that I see it. Okay. So the convergence of these expansions is completely determined by the properties of these random tensors here. Okay. Okay. So what I didn't say is that, okay, there is some little things in which we have to weak order the sort of the nonlinearity, and this is because and if you can have an infinite mass, L2 mass, which means that then your potential energy is infinite, and so you cannot make sense of the nonlinearity as distributions. But this is rather standard how you renormalize the nonlinearity, which is this weak order, which is done all the time in sort of stochastic PDE and quantum field theory. So I don't want to talk too much about this. And the uniqueness that I mentioned in the theorem comes from the fact that our solutions are the unique limit of any possible choice of approximations that you can think of. You can choose any regularization you want, and the solutions are the unique limit of that approximation, and that's the uniqueness we have. And so let me give you a picture. So in this picture, this is the deterministic scaling, and this is what was non-deterministic. The green was what was non-deterministic. And what is it that we are proving? Well, we are proving actually that in the probabilistic sense, if this is the probabilistic scaling, we actually can prove local Well poses all the way from here all the way up. Okay. So in the case of Bourgain in '96, what he dealt with was with the cubic equation in 2 dimensions. So if you are cubic and you're in 2D, then this number is exactly 0. Okay, so this green bracket becomes 0. And what he proved is that if you're a little below 0, then you have solutions. But in that case, that's the supercritical relative to the deterministic scaling. And so in this theorem, we actually can go all the way here. We don't go just a little bit below, but we go all the way. And I should say that between Bourgain's work and our theorem, there has been an enormous amount of work where people were getting different results. They were going in the supercritical regime relative to the deterministic scaling, and they were obtaining different types of results. And so the question is, okay, you know, how low can you go? I mean, what is driving this? And the answer is this probabilistic scaling. And this is a definite answer that tells you that, okay, in this full subcritical regime relative to this probabilistic scaling, you always have local well postness. So the second result I don't want to mention too much because I'm going too slow is that we also have some sort of long time results. And I just, this is more linked to the theory of wave turbulence, but actually, if you prepare your smooth data a little bit better, in which you take not just the random variables, but you put this smooth factor, right? I mean, so that your Fourier modes are sort of uniformly distributed on the unit ball, on the ball k less or equal than n. Then for this type of data, we actually get not just local well postness, but we get long time. We get that for a very long time, a time that is like this, you have solutions. So let me skip this slide, but this is just to say, this is actually a corollary of the previous theorem. So let me talk a little bit now about Gibbs measures, okay? So Gibbs measures come when the alpha that you take here is 1. I mean, okay, so if you take alpha equals to 1, then this is always the typical element, the support of a Gibbs measure associated to the nonlinear Schrödinger equation. Now, in dimension 1, then this is still a function that belongs to h½ minus, it's still a function. But if you're in dimensions 2 or dimension 3, then this is not anymore a function, it's a distribution that becomes rougher and rougher as you increase the dimension. So in dimensions 2, you're just below L2, but in dimension 3, you are in H minus a half minus, you're very, very rough, okay? And so, so these measures are important for many reasons, but also one particular is that they correspond to the stationary solutions in the wave kinetic theory, okay? But anyway, so the Hamiltonian structure of, so the fact that you have a Hamiltonian associated to the nonlinear Schrödinger equation tells you that formally, okay, from what you do in finite dimensions, you could define a Gibbs measure as the exponential of minus the Hamiltonian times the Lebesgue measure. So in other words, the Hamiltonian has a kinetic part, it has a potential part. So you take the kinetic part, you put it with a Lebesgue measure that gives you a Gaussian measure, and then you separate the potential part, and you want to think of this Gibbs measure as being a weight. You want to think of this as being a weight of a Gaussian. So you want to think of this as being a weighted Gaussian measure. So this is just, I'm just waving my hands. All of this is formal, and as I said, as written, none of this makes any sense. So the question is, one can you actually make this formalism rigorous? And this formalism actually should tell you also that the measure is invariant because the Hamiltonian is conserved. And somehow Liouville's theorem should tell you that the Lebesgue measure is volume preserving. So you expect this measure to be invariant, okay? In the sense that if I take an initial measurable set in the support of the measure and I flow that set with the dynamics of my equation, then I would like to know that the flow set has the same measure as the original set. So when can you do this? Okay, so the first question is, before I talk about the dynamics, the question is about when can you construct these measures? And so this construction and all the properties, okay, has been a major problem in statistical mechanics and constructive quantum field theory. And when P is 3 is intimately related to the so-called phi4 model, okay? So the construction can be done in dimensions 1 and 2 for any P, and in 2Ds due to Nelson. And what you obtain is that indeed the measure is absolutely continuous with respect to the Gaussian, that this is indeed the weight, is locally integrable with respect to the Gaussian, okay? So that's true. In dimension 3, the construction can only be done for power 3, but not for here can be done for all powers, but here only for power 3. This goes back to Glimm and Jaffe. But there is another obstacle, which is that the measure that you obtain is not absolutely continuous with respect to the Gaussian measure. So this is not true. This is not true, okay? So, so it's actually singular. The measure is actually singular. This measure mu is singular with respect to the Gaussian measure. But there has been recent work of Barashkov and Gubinelli that gives us a better understanding about how this measure, what is the description of the support or the statistical ensemble of this measure. Maybe I'll say something later. And then when this bigger or equal than 4, then this cannot be done for any p. You obtain what is called the marginal triviality, and I'm not going to say much more about that. So in dimensions 1 and 2, what about the dynamics? So in the dynamics, I mean, so now I'm going to talk about the invariance of the measure together with the existence of global strong solutions for data drawn from the measure. And so, as I said, the difficulty in studying the dynamics comes from the fact that in dimensions 2 and above, you are in a very rough space. If you're in dimension 1, you have a deterministic local well-posedness, there is no problem. But in dimensions 2 and 3, you have a big problem because the data is very rough. Okay. So in dimension 1, for any p odd, the invariance together with the global well-posedness was proved by Bourgain in '94. And in dimensions 2, but only when P is 3, is this paper that I mentioned before of Bourgain in 1996, which actually is one of the most important papers I have ever read. It's a very important paper. Now, the point is that and it's the paper that initiated all of this random data theory. And so the point is that the measure can be constructed also not just for p equals to 3, but also for p equals to 5, 7, 9, whatever power you want to take. But nobody knew if you can actually prove the invariance and the existence of global strong solutions on its support. So this was an open problem since Bourgain's work until 2019, when we solved it together with Yudeng and Heike and Yue. So in fact, we proved that for any p bigger or equal than 5, in 2 dimensions, the measure is invariant, and we always have the most surely we have this existence of global strong solutions. Okay, so this essentially closes all cases in dimension 2. So what is left then is simply what happens in dimension 3 with the cubic. Okay, and this is yes, is a question? Okay.
No.
Okay. So this is actually still open. It's a still open problem, and it's very, very hard. But let me tell you, why can we solve this problem and not this problem, right? If you look at the deterministic scaling, this problem in dimension 2 and the quint, so if take p equals to 5 and dimension 2, the deterministic scaling, the scaling is 1/2. If you take dimension 3 and p3, then the scaling is also 1/2. Okay, so how come that you can solve this and you cannot solve this? So if you only put yourself if you only look at the deterministic scaling, then you don't understand why is it that you can solve this and not this. And the answer is actually in the notion of the probabilistic scaling, and the reason is because in the probabilistic scaling, if you take the quintic, the probabilistic scaling of the equation is going to be -1/4. And the measure is going to be supported just below L2. So in other words, the measure is supported above the probabilistic scaling. So this problem is still what we call probabilistically subcritical. While in dimension 3 with P3, then the probabilistic scaling is -1/2. Okay, and -1/2 coincides to where the measure is supported, because the measure is supported in -1/2 So somehow now the problem becomes what we call probabilistically critical. So this is probabilistically subcritical, and this is for any power p is probabilistically subcritical, because -1/p-1 is always below 0, while here the problem is critical. And so that's actually the reason why these two problems are different. Okay. So this is essentially stating the theorem that we prove in the rigorous term. So I just said that we prove, this is what we prove. Let me not repeat it. Let me just show you the picture here. I mean, this is the meaning of invariance. Okay. So the picture here is that you know, Bourgain, when the dimension is 2 and the p is 3, when the power is 3, what Bourgain proved was that the measure is supported here. So SG is 1 minus d over 2. Remember, this was related to the statistical ensemble. This is, and so this tells you that then the support of the measure is in SG minus. So it's just, so when p is 3, so sorry, for any p in 2 dimensions, this is always below L2. And so in order for Bourgain to be able to solve this problem, he had to somehow start from something that is below the deterministic scaling, which is L2, and somehow manufacture some smoothing to be able to jump and get into something which is above L2. I'll tell you more in a minute. So in other words, he had to manufacture some smoothing out of nothing because the nonlinear Schrodinger equation gives you no smoothing whatsoever. Now, when p is bigger than 3, then the deterministic scaling is here. Remember that if I am above the deterministic scaling, I have local wave closeness from the deterministic theory. So when p becomes higher, it's almost as if you have to manufacture more and more smoothing out of nothing. So that's another reason why the problem is harder and harder. Okay, and the probabilistic scaling is always here. Okay, so this is what we prove. Okay, and so let me actually tell you about Bourgain's method. So in Bourgain's method, what he did is he considered the way that he did it is he said he introduced this notion of having an ansatz of like what we call a linear nonlinear decomposition, in which instead of trying to find the solution u as a fixed point on some ball of a function space, you say, well, no, I'm going to look at functions u that can be written as the linear evolution of the random plus a term v, okay, which you want to prove that has positive regularity. So this function is below L2, so is in H0 minus, and you want to show that this v actually is with positive regularity. And so you want to do this linear nonlinear decomposition. And so he made this answer. And so what is v? V is the solution of the difference equation, where now this is for cubic. I put c instead of cubic because the equation is renormalized. But then now you see your cubic equation is going to have interactions of linear evolutions of random and of this v. And so whenever you have, say, 3 terms, whenever you have only interactions of the linear evolution of the randoms, then sort of the multilinear large deviation estimate tell you how to estimate this term. When you have only interactions of the v term, in your answer, you're assuming that this is going to be above L2. So then you have the deterministic theory that tells you that you can control the interactions of only v terms. So the real problem is when you have interactions of both of them. So for example, when you have 2 of these and 1 of these. So then you see, if you have 2 of these and 1 of these, then you don't have independence between these 2 things. So you cannot use directly the multilinear large deviation estimates. And so what Bourgain did was he actually used what in harmonic analysis called a TT star argument, or he actually did a random matrix estimate, which is actually the correct way of exploiting randomness when you have in the absence of a gain of regularity. And essentially, I don't want to explain too much about what it is, but it's actually quite intricate, and it's actually a very important idea, okay, that you need for Schrodinger. And once he proved this, so he actually proved exactly that then you have a local in time solution that has this form where this v is in some hs with s bigger than 0. Okay, local in time. And once you have this, he has a globalization argument, which is pretty standard and is based on the fact that when you truncate your Gibbs measure, then you know that the truncated Gibbs measure by itself, because it's a finite dimensional one, is invariant, right? Because you truncate the Hamiltonian, and so the corresponding truncated evolution is still Hamiltonian, and the measure associated to it is going to remain invariant because this is still preserved, okay? So you use the invariance of the finite dimensional approximation of the measure to actually extend the local in time finite dimensional solutions into global solutions. And then once you have done this, you use this to extend the infinite dimensional, the limiting solution into global in time. So this is done in 4 steps. Maybe I don't want to read all of this because this is essentially what I have just said. And maybe I should say that it's very important that when you prove these global bounds for the truncated systems, these have to be uniform in the truncation parameter. And you want also global bounds, not just on the solution, but also on the individual components of the answer. And then once you have these, then you prove the global well-positiveness of the full evolution. And you also need some stability arguments because, you know, when you go from 0 to tau, when you are at tau and you want to restart, then your data has changed, right? Has changed, it's not anymore the linear evolution of your random. It has this smooth error, and so you want to prove some stability under small smooth perturbations of the data to be able to continue. Okay, and then at the very last, once you have the global well-positiveness, then you take the weak limit of the measure and you prove the invariance of the infinite dimensional Gibbs measure. And usually in this globalization argument, the second step is the hardest one to do. But in one way or another, you can somehow implement this globalization argument. So I'm not going to talk about global anymore, because what I want to say is that the heart of the matter usually is always in trying to get the local well-positiveness. Once you have the local well-positiveness, somehow, at least in the cases in which you know that the measure is absolutely continuous with respect to the Gaussian, you can implement one way or another one this globalization argument. So, so what's happened in the quintic case? So in the quintic case, the problem that you have is you try to do the same thing as Bourgain. You try to do a linear nonlinear decomposition, but then the problem is now, okay, you're still, the measure is still supported in H0 minus, so the linear evolution is still in H0 minus. And the V, but the problem that you have is now you cannot place the V in a deterministically subcritical space. The best you can do with this V is putting in H1/2 minus, okay? And so in order to run Bourgain's argument, you would like this V to be in H1/2 plus. But there is no way that you can put it there, no matter what you do. So when you try to understand what's going on, you said, well, where the poor regularity of this V come from? Well, like in all these problems, the poor regularity comes from the high-low frequency interactions. So you say, well, this V, Bourgain treated it as a deterministic, but this V is a random. So what if we peel off some random structure from this V that allows me to say that after I have peeled it off, if after I have peeled off the bad interactions, then what I have left is indeed in H1/2 plus. But you know, when you try to do that, you know, so you try to identify what I just said is that you try to identify the term that I call X, which is somehow the Duhamel between the high frequencies of the linear evolution of the random and then the low frequencies of the p-1 powers of U. And then what you would like to prove, what you would hope, is that somehow X behaves like the linear evolution of the random, and that when you subtract this X from the V, what you have, the Y, is actually smooth, it's above H1/2. But the problem is that in order to control this, you need to have some control on the low frequency parts of this. You need to have some a priori control of this. And but this term in itself has contains the p-1 powers of the X, okay, whose regularity is in H1/2 minus. So, and I can iterate this as many times as I want, or I can do, you know, any trick that I want, but I will never get out from the fact that I don't have enough regularity in this term. I don't have, in the low frequencies, I can never do any better than H1/2 minus. So peeling off this term doesn't work. This is exactly what happens in the heat equation and or even in the wave equation, in which the better sort of like smoothing properties of the Duhamel allows you to put the low frequencies in a better function space, and then by separating a term like this, you can actually close your estimates. So with the linear, some para-control terms plus a remainder. Okay, but in the case of Schrodinger, you're stuck. You cannot do this because you're always, no matter what you do, you can never, you're always in H1/2 minus. Okay, so there is no way of controlling this, doing this. So you have to change your paradigm, you have to change your point of view. And this is what the method of random averaging operators that we introduced in 2019 to solve the Gibbs measure problem does. Okay, and this method of random average operators, in some sense, was the precursor of the random tensor theory that we used to prove the first theorem that I told you before. And so the method of random average operators is sort of less notation heavy than the full random tensor theory, and is linked to the first random tensors, which is what we call the 1-1 tensors. So let me tell you a little bit about the random averaging operators. So suppose that, I mean, let me take the cubic case because the quintic is very hard to draw. And so what is a 1-1 tensor? So what you do is I is always the Duhamel operator. The dark blue is the linear evolution of the high frequencies of the random data. And the light blue is the low frequencies of your solution. And I'm going to define this graphical notation, the Duhamel of the cubic term of the linear evolution of the random and the low frequencies here and here. And then I'm going to iterate. I'm going to take this and I'm going to put it in the first component. And then I'm going to have the Duhamel of the cubic term of the Duhamel of the cubic term. So I'm going to start iterating this tree sort of by expanding. So what I'm doing is I'm expanding the nonlinearity using the equation itself, right? And I'm going to do all of this. And I keep on doing it on the first component all the way down, okay? So if you do it all the way down, then you ask, well, what is the sum of this blue plus all these terms? Okay, so what is this sum? Let me call it a blue cube, and I'm going to call it this function psi n and delta. So what happens is that this sum is equivalent to the solution of this paralinearized equation, where in the first component I have this, and initially I have my sort of high frequency, sort of the end frequency of my data. And so you can solve this explicitly, and what that tells you is that somehow the solution to this problem on the Fourier side is exactly the sum of a matrix, which is what I call a 1-1 tensor, is a matrix times a Gaussian. So what is it that I'm saying? I'm saying that the solution to this problem on the Fourier side looks exactly like a color Gaussian, because this random matrix is actually very nice. Okay, and so what is the ansatz or the random operator ansatz is that you say, well, I'm going to write my solution not as Bourgain, which is linear plus remainder, but I'm going to write it as the linear evolution plus a random averaging, an operator acting on the linear evolution of the random data plus a remainder. And as it turns out, okay, this is as smooth as your data. This is still going to be in h½ minus now, but you can prove it. But the remainder now, it is indeed better. It's going to be in h1 minus, okay? And so in some sense, what we are doing is we are viewing the key high-low interactions as that come from the linear evolution of random as an operator applied to this. So we don't view it as a para-control term, but we view them as an operator altogether. And if we expand the solution in Fourier space, we have an explicit expansion. We know that, okay, at zero or at zero order, you have the linear evolution of random. And then what you have is a color Gaussian. So you have this matrix is actually almost diagonal. So you have a Gaussian that is a little twisted by this matrix, and then you have a smooth remainder. So I'm giving you a description of the solution to first order, a very precise description of the solution, okay? And this tensor is going to be independent with this Gaussian, okay? And it's going to carry, as I said before, the low frequency, the information of the low frequency components of your solution. And so the whole point is that you have to prove suitable estimates for this. Okay, so I still have 15 minutes, no? I can't remember when I started. Felipe?
Well, you have 10 minutes, I think. 11 minutes, okay.
Okay, I might go like maybe to 15 if it's okay.
Okay.
Otherwise, I'll have to skip some stuff. Okay, so let me tell you the theory of random tensors. Okay, what it means is that if you want to solve the problem all the way to the the 2D Gibbs measure, as I said, was subcritical, but there was still a gap between the scaling and where the measure is. But if you want to solve the problem all the way to the subcritical probabilistic scaling, then this leads naturally to have higher order expansions and sort of multilinear expressions. So in other words, I need more than just 1-1 tensors. I need what I call the Q1 tensors, okay, which are going to, so these tensors are going to depend on the low frequency components of the solution. So the tensors come exactly from these high order iteration trees, okay? And so let me give you an example of what is a 2-1 tensor. So what does it mean? It means that now, instead of having one terminal leaf that is the linear evolution of random, I have two terminal leaves that are the linear evolution of random, and one that is the low frequency of the solution. So in this picture, okay, the frequency of N1 and N2, if the maximum of these frequencies, if n is the maximum, each of these frequencies, if I call n the maximum of these two, then these frequencies are always larger, much larger than the frequency here. So these two are much larger than here. Okay, and so what is on the Fourier side, this 2-1 tensor? When you see now on the Fourier side, if you take the Fourier side of this object, what you get is the sum. So this comes from the Fourier coefficients of taking from the relationship of the linear evolutions. Then what you have two randoms, so it's going to look as the sum of k plus k minus k2 plus k3. This is the resonant factor. Then you have your two Gaussians, and then you have the low frequency here. Okay, and so if I put this as a characteristic function and I collect all of this here, then the k3 is always a small frequency. The k1 and k2 are large frequencies. And so if I put this inside here, and I call all this term is what I call hk k1 k2. Okay, so I view this as a mapping of k1 k2 into k, and this is what I call a 2-1 tensor. Okay, and I view it essentially as a map. But it's just an example of a 2-1 tensor. Another example could be if I had actually taken a picture of this form, in which I have the linear evolution of random in the first entry, then I have the Duhamel of the Duhamel, and I have the linear evolution, then low frequency. Then in the second entry, I also have Duhamel of the linear evolution, low frequency, and third entry, I have all low frequencies. So then the Fourier transform will look like this, and this is also an example of a 2-1 tensor. Okay, so there's many manifestations of 2-1 tensors. And so the random tensor theory, what it does is allow us to handle sort of this exploding complexity that arises from the high order iteration trees when you start to higher. So you're going to sort of like iterate, and you're going to stop iterating a factor when this factor reaches a low frequency, something like un to the delta, right? And if not, you're going to keep iterating. But this is actually a total mess. And so this organization in random tensors is what allows us to control the complexity of this process. And what I should do is that this tensor is exactly the counterpart of Martin's Hare regularity structures for singular parabolic SPDE. So it's the dispersive counterpart to this theory. And in both cases, the whole point is features a study of the problematic high-low frequencies. And while in the regularity structure theories, what it features is a Taylor expansion, which is locally in time, right? And is expressed in terms of multilinear Gaussians. And what we have is also an expression, but it's on the Fourier side in terms of multilinear Gaussians. So it's kind of there is this parallel. And so what we do is we develop an algebraic theory to handle these tensors, which is the merging and trimming. We call merging and trimming of tensors. The merging is what allows you to build the larger tensor from the small tensors. And trimming is something that you do so to after you have merged, you have to always guarantee that in your answer, these two things remain independent. And this is what the trimming operation does. And then what we do is we develop an analytic theory, which entails choosing suitable norms for these tensors, which behave well under the algebraic theory of merging and trimming. And we proved several multilinear estimates for this. The bounds are all L2 based. And essentially, one is kind of like a merging estimate. So that tells you how to control the norm of these merged tensors. And the other one is actually the analog of Bourgain's TT star argument, which is what we call a trimming estimate, but also can be called like the moment method. And once we have this in place, then the proof proceeds by induction, relying on these two theories: large deviation estimates, some sort of elementary analytic number theory, and a very subtle selection algorithm that tells you which is the best way of choosing which multilinear estimate to choose. We have a broad range to choose from, and you want to know which is the best one to choose at each step. So there is a combinatorial argument that allows you to exploit the flexibility that we build in the multilinear merging and trimming estimates to prove a theorem. So here are some examples of merging. So, you know, it's like you take here a 1-1 tensor, 2-1 tensor, 3-1 tensor, and this gives rise to a 6-1 tensors when, say, there is no pairing, so none of these frequencies are the same. So if this frequency is the same as this one, then you need to contract, okay, against the Gaussian. So instead of getting a 6-1 tensor, you're going to get a 4-1 tensor, okay? So this is essentially merging. And trimming is kind of like what happens after merging is that it can happen that these are all the Gaussians that they fall, the frequency of this fall below your n delta. So that will break the independence. So what you want is to trim this, that's the trimming by contracting against these Gaussians. And so the tensor that you obtain remains independent of the Gaussians that are here, here, and here. So by doing this contraction, which is this picture here, then you guarantee that these objects, the tensor that comes from this object, and this object, which is H prime K A B C, remains independent of A, B, and C. Okay. All right, and the merging estimate, as I said, I'm not going to kill you of this. This is what is called the merging estimate. Let me just tell you why you have a lot to choose from. Is because when you write a tensor here, the order in which you write these tensors don't matter, but the order in which you estimate them do. So you have a lot of flexibility as how to estimate these tensors. These are L2 operator norms. Okay. And so when you're running your inductive argument, somehow you have to choose which one is the most suitable one, okay? And there is a combinatorial argument to do that. And the trimming estimate actually, which probably as written doesn't tell you anything, but tells you essentially that when you have trim a tensor, when you have a tensor that comes from the trimming operation, then you can bound this operator norm by a small loss times the maximum of all possible merging estimate norms for this age. Okay. Now this is actually something which is very basic in the study of random matrices with general Gaussian entries, but we couldn't find the proof of this anywhere, even in the simplest cases. And the proof of this is goes back to Bourgain's and to sort of high order iterations of his TT star argument. Okay, and this is what gives what we call in this paper trimming estimates, but can also be called a moment method estimate. Okay, so once you have all of this in place, then you can actually close your estimates, because you can now sum this answer. Because what you do is everything that we have done is to actually prove the correct bounds for the tensors that tell you essentially that you have a little bit of a growth. This beta is less than alpha, so this growth is going to get killed by this decay, and this gain that you have here is what is going to allow you to sum this Fourier series. Okay, and then you close your estimate. And we prove not only these estimates, but we also prove some weighted estimates that tells you that these random tensors localize as Fourier multipliers. So this is what I was telling you before. So suppose that little q is 1, then you have here a matrix. Then these weighted bounds tell you that matrix is almost diagonal. So that somehow this is really to first order, if k is 1, like a twisted Gaussian, like a color Gaussian. And when you go higher in the order, then they remain. So you will have it, say, in the 2-1 tensors, it will be like a cube, and that cube will still localize on some diagonal hyperplane. And so you have a very precise description of the solution. And so let me finish in the last 5 minutes with some open questions. So the open questions that I have is the first one is we prove a theorem that is the best possible theorem for probabilistic local well posedness, but it's a local theorem. And so what you want to know is well, how do you globalize these theorems? I mean, if you have random tensors or random averaging operators, can you sort of globalize these random tensor structures? So when you have a Gibbs measure, okay, then this globalization is possible, like I show you. So Bourgain did it in 2D, okay, and we did it in 2D for the cubic one, and we did it in 2D for the any power odd power, by essentially following Bourgain's globalization plus a stability theorem that tells us that our random structure is preserved as you move from one type step to the next one. Now in 3D, because the singularity of the measure, the globalization argument is actually expected to be much harder than just Bourgain, and this can be seen in works of Brinkman and Okamoto Tolomeo, who studies sort of the nonlinear wave equation with a Hartree type nonlinearity. They did it in the stochastic, he did it in the random data sense. So okay, so if there is a measure, you have some hope. I mean, in 3D, if the measure is singular, it's harder, but there might be something you can do. But if there is no Gibbs measure available, then all bets are off. Then it's not clear how to globalize this argument. So if you take something like the cubic NLS in 3D, okay, with data that is much smoother than the probabilistic scaling, as take it to be in L2. Okay, the probabilistic scaling is -0.5 for the cubic here. Take the data in L2 or even above L2. Then, how do you globalize? It's not clear. Okay, it's not clear how do you globalize any of this, or whether any part of the description of the solution of this random structure can propagate for longer times. Okay, so okay, so there is the big question left for the NLS, for the cubic NLS, which is the invariant. This is actually after our theorem in 2D, which completed all cases. This is for the NLS. This is the only case that is remaining, which is the how to prove the invariance of the 3D Gibbs measure for the cubic NLS flow. And as I said, there are two major issues now. One is that this is probabilistic critical. Okay, the support of the measure is here, and now the probabilistic scaling is -0.5. So this is a probabilistic critical problem. And then you have the problem that the measure is singular with respect to the Gaussian, which means that you lose the independence of the Fourier coefficients of when you take a sample in the statistical ensemble. Before, we used very strongly that when you take a sample, when you sample from the support of the measure, you have your samples have independent Fourier coefficients, right? We use that very strongly. Here you lose that. So you have two problems: the roughness plus the issue of the loss of the independence, right? And so so you have a big problem in the local theory and also in the global theory. Let me skip these two things, and maybe just say that what I said before, that although the measure is singular, this recent work of Barashkov and Gubinelli actually tells us a little bit that yes, these two measures are singular, but the measure mu is an absolutely continuous perturbation of a random shift of the Gaussian free field. So it tells you not only that they are mutually singular, but it gives you a little bit a better description. It tells you that it's somehow a shift of this Gaussian measure. Okay. And what this tells you is that somehow, okay, the Gaussian part is somehow in the description of the measure you have a Gaussian part plus other terms which are a little bit better, but somehow the Gaussian part is the one that still presents the the main difficulties. And but this is a hard problem and is still open. An intermediate problem, okay, without treating the intermediate in the following sense, in the sense that instead of being in 2D, you are in 3D Gibbs. So you have the same two problems. This problem, you have you still have the roughness of the data, but instead of being probabilistically critical, you are probabilistically subcritical. But you have the problem of the measures. And a problem that is a little bit easier than this is to treat the case in which you study the 3 Gibbs measure under the cubic nonlinear wave flow. And the reason why I'm saying that is easier is because for the wave equation, the probabilistic scaling is not -1/2 like in Schrodinger, it's -3/4. And the measure is still in -1/2 So now you see this problem for the wave becomes again subcritical instead of being critical. Okay, and so you still have the problem of having lost the independence of the Fourier coefficients, and you still have a very rough data. And so this actually is a very hard problem, and actually we were just able to prove this, and this is a theorem. The paper should be in the archive by early next week. And we proved that the cubic nonlinear wave equation is almost surely global wave pulse with respect to the Gibbs measure, and that the Gibbs measure is invariant under the flow. And so this result is actually what we call the hyperbolic counterpart to the parabolic phi-4-3 model, which was solved by Herr and Mathematicians. Okay, and I don't have time to give you some of the ideas of how we prove this. Maybe I should just say that because you're subcritical, your first thought is, okay, you can just apply the random tensor theory to get the local, but actually that's true, but you don't need to do that, and that makes the problem conceptually much more intricate. You can actually go back to ideas of the paracontrol calculus and make an ansatz that is not given by the random tensor ansatz, but by this paracontrol type ansatz. And so you have two challenges. The first challenge is to find a good representation for the statistical ensemble of the measure. And we achieved this actually by using an associated cubic stochastic heat equation. So this brings out a very, very nice and a very sort of a surprising interplay between the parabolic and the hyperbolic theories. And the second sort of challenge is to find the right ansatz. And as I said, we don't use this because we don't need it, but we use instead the paracontrol ansatz. But we do use the analytic framework of the random tensor theory. We use some deep analysis that comes from the work of Deng and Hani for the full derivation of the wave kinetic energy, and plus some new Q ingredients like some hidden cancellations in the sort of stochastic objects that appear in the representation of the ansatz, and a new bilinear random tensor estimate that goes beyond our random tensor theory. And so let me just apologize, because I did went out of time, and thank you very much.
Okay, thank you very much, Andrea. Okay, so we have time for some questions. So anybody?
Should I stop sharing so I see, or?
Yeah, probably, yeah.
Let me see. It doesn't let me. Oh, now it does. Okay, so now I can see.
Okay, any questions?
Let me put gallery so I can see everybody.
Andrea, I have a question. So in the settings you work, you always use the tori, right? So
yes.
Okay, so that's the first approach, or you have some set you want to work with?
So certainly some, for example, for the 2 degrees measure, certainly that can be done, not just, you know, you can extend these results for irrational tori. I mean, so that you can do. Now, in another settings, that's a very good question. And so the first question is actually how to do this in Euclidean space. I mean, you know, can you have a corresponding random tensor theory in Euclidean space? I think that's a very important question. And then how to do it on manifolds becomes, you know, is actually a very difficult question, because here we use sort of the counting estimates, or the analytic sort of number theory comes in very, very strongly to prove our results. And instead of that, you will have to rely not on this random Fourier series, but on sort of these eigenfunction expansions. And so then, you know, you're constrained by the best estimates you can prove for your eigenfunctions, right? So so that's in terms of changing the manifold, the underlying domain. Those are the things I can think of. But there is actually promise in which you can actually try to study these problems for geometric flows. So instead of so in which you could still take periodic in the domain, but you go into some manifold. And there is some work in this direction that was done recently by one paper is by Brinkman with Luhrmann and Stafilani, and the others, which is for, but that's local, is a one-to-one wave map, Maxwell Klein-Gordon equations, and that's by Krieger, Luhrmann, and Stafilani. That's for small data global work-closeness, actually. But in both, so in the first paper, in the first paper, they use our random averaging operators ideas. And in the other paper, the one by Krieger, Luhrmann, Stafilani, they just use Bourgain's linear nonlinear decomposition. But in the last one, in the 1+1 wave map, they cannot get global yet. They just get local, but they use the random averaging operator ideas.
Okay, Andrea, there is a question from.
Hi, Anna.
Hi, Andrea. Very nice talk as always. I have a quick question. Is there any hope to be able to do bounded domains or domains with boundary?
Yes, that's actually what I was just saying, that, you know, is the question here is how do you, I mean, that you're going to be is a very good question, because it's actually a very useful question. And the idea there is that you have to start developing a theory in which, you know, you have to replace, you know, the power of the analytic number theory that we use by, you know, now you have eigenfunctions, right? You have the corresponding, you know, Laplace-Beltrami operator, it has its own eigenfunctions, you have your own expansions, and you're constrained by the best possible estimates you could prove for your eigenfunctions. So, you know, something should be possible, but, you know, okay, it doesn't have to be.
If you use a ball or a disc.
Definitely, definitely, that would be fantastic. Yes, yes, and actually, you know, using Bourgain's linear nonlinear decompositions, there are results actually on 4 domains. There are results by I should say by Berg and Setkov. They did it for the nonlinear wave on a ball, on the boundary of a ball. There is, I mean, it's escaping me, but there is also a work by Bourgain with Boulou, which is also for the ball. And then there is some recent work also by a student of Nikolai Berg, Nicolas Kamps, which also does it for a ball. So using Bourgain's original ideas of linear or linear, there has been some work. In the last work of Nicolas Kamps, I think he still uses linear nonlinear. Some people have started to use the random averaging operators ideas, but what they have done actually, I'm not sure if it's for a ball, or what they have done actually is they have actually considered fractional Laplacians instead of Laplacians. So this is work by Chen-Min Sun and Sun and Setkov. But so people have started to sort of try to get results. So the method of random averaging operators is much easier to use, right, than the full random tensor theory. But it's a fantastic question and a one that is needed, right? Yeah.
Thank you.
Sure.